Dr. T.V. Geeta, Professor, Department of Computer Science, College of Engineering, Guindy, Anna University. Her special interest, Artificial Intelligence and Natural Language. She has published more than 143 articles in national and international journals. She has guided around 7 PhD students. She has got Young Scientist Award from Government of Tamil Nadu in the year 2000, Chief Minister's Special Mention Award in the year 2002 and Woman of Excellence by Rotary Club in the year 2003.
Welcome to the UGC lecture series. In this lecture we are going to talk about graphs, some definition of graphs and some operations that we basically do on graphs. So that is what we are going to see in this lecture. So first let us look at what a graph means. An example of a graph, you can see an example of a graph here. A graph is used in a number of places and it is one of the very most important and naturally occurring data structures, you can call it, because anything on you can you can represent using a graph. For example, this the example that I am going to show you will represent the different cities and maybe the flight between the cities or the roads between the cities, maybe trains between the cities and so on. You can also represent a network of power stations and the network and the places where it covers. The power stations can be represented by a network. Similarly, network or a graph. You can have many such examples in your life that would be represented by a graph. Okay, so let us take but for mapping sake and for understanding sake, if you look at a graph as the nodes and edges to represent the cities and the routes between them, it would be easier for you to understand the algorithms, but it is applicable to any application that you take. Now let us take this example. This just shows you different cities and the maybe the distances between them, it could be the routes between them, whatever. So this particular example showed you flights. And similarly, you can have another example of computer network or the internet. So this again shows you that these are nodes that UNT has, these are nodes that Intel has, and so on. And this is a connection between the between all the nodes. So this could be a regional network and so on. Now, if you take an application, a typical application of a graph, which is very famous as a graph application, is a traveling salesman problem. And the idea was to find the shortest path that connects all cities without a loop. Without a loop means you do not come back to the same city again. So if you take these nodes to represent cities and these to represent the paths, then so you are assuming that from all cities you do not have paths to all other cities. So this is a typical example. So suppose you want to start from here and come back here without visiting any node more than once, this is probably the path you will take. You will go from start, go here, go here, go here, go here, and finally you reach back the start. So this is a typical example. Now if you want to find out whether this is the shortest path, now in this particular example without a loop this is the only path you can go through. Now with a loop but you want the shortest, then maybe this would be the better one. We do not know. We have to check up. For that you have to know the what do you mean by shortest again? It could be the cost or it could be the distance, cost of travel, distance of travel, time to travel, it could be anything. So depending on that you can put a factor here and depending on that you have the shortest path. Now let us look at some concepts that are associated with graphs. Now this the circles normally marked as circles are either called a node or a vertex, and the lines connecting the nodes or vertices are called edges. The edges, there are three properties that the edge can have. The edge can be unidirectional, can be directional, can be associated with a weight, need not be associated with a weight. So you can have edges of that sort. This we have taken a simplest case where we do not have anything, it is just a unidirectional edge. So now let us go. A graph now G is represented by V and E. Please note V stands for the vertices and E stands for the edges, and it is composed of V, that is a set of vertices or nodes, a set of edges or arcs, and these edges connect the vertices in this set. So you have two sets, vertices set and an edge set. An edge is usually represented as UV, where UV are all vertices belonging to this big set V. Now, if you take an example again, the V's are A, B, C, D, E, these are the vertices, and the edges here are AB, AB, AC, AC, AD, AD, BE, BE, CD, CD, CE, CE, and then DE. Please note, not directed. You can say this edge is A to B and B to A. In this example where we have taken, you can it goes both ways, but here A to B and B to A we have not written it as separately. In normally in undirected graphs, if you have A to B, we are assuming that B to A happens, and we do not represent it as separately as an edge. So, now let us go to undirected and direct graph. Now, look at this example. This is an example of the same graph. Okay. This is an undirected graph, I mean same nodes. This is an undirected graph which has edge has no orientation at all, while the directed graph which has an edge which has orientation, or it is oriented towards a vertex. So, this says that you can go from here to here or here to here. This says you can go only from here to here. There is no possibility of coming from here to here. So, this is called an undirected graph, and this is called a directed graph. Now, let us look at the next term. So, now we have seen a graph, we have seen vertices, we have seen edges, we have seen two types of edges, edges which are directed or has an orientation, and edges which are unoriented or does not have an orientation. Does not have an orientation was called undirected, what has an orientation was called directed. Now, let us take the degree of a vertex. The degree of a vertex is the number of edges to that vertex, and for a directed graph, it is the in degree of a vertex is the number of edges that has V as the head of the. So, there is a difference in how you talk about degree in the case of an undirected graph and the case of an directed graph. So, here you have degree. Degree is the number of edges to that vertex, and in degree is the number of edges which has that as the head, and out degree is the number of edges which go out from that node. The out degree of a vertex V is the number of edges that has V as its tail. If di is the degree of a vertex I in a graph G with n vertices and E edges, the number of edges is given by this equation. Okay, n vertices and E edges, then it is given by this equation, and adjacent because adjacent vertices are counted twice. So, that is why you are normally having this by 2. Now, you also can define some term called subgraph. The subgraph is actually a component of the graph. So, for example, you have this part alone becoming a subgraph. You can have this part alone becoming a subgraph. You can have this alone becoming a subgraph, and so on. Please note, again we have taken a case of an undirected graph. You take a case of a directed graph, it may be slightly the definition will have more subcomponents possible. So, now let us talk about a path. Now, a simple path is a path such that all vertices are distinct except the first and the last, which could be the same. For example, A, B, C, D is a path, and then you have a cycle. A cycle is a path that starts and ends at the same point. For undirected graphs, the edges have to be distinct. For example, this is a cycle. So, you have C, B, D, C. If it comes back to C, it is called a cycle. Okay. So, for undirected graphs, these edges that we talk about CB, BD and DC are distinct. Okay. So, that is a cycle. Now, we have connected and unconnected graphs. For example, this is a connected graph. These three nodes are connected, but this node is a node which is not connected. This is a connected graph, and this is an unconnected graph because this node is in isolation from the other nodes. Okay. So, we have a connected and unconnected graph. So, now again let us look at the different way of more formally talking about undirected and directed graphs. In an undirected graph, the adjacency matrix, which we are going to define as we go along, is symmetric. That is, every term Aij is equal to the term Aj. Okay. and in a directed graph this is not necessarily true. The adjacency matrix may or may not be symmetric, but it is not necessary that it has to be symmetric, and Aij is not necessarily equal to Aj. I will talk about what is this Aj and Aij as I go along. Now you have something called a directed acyclic graph. A directed acyclic graph, this is a special type of graph which has lot of applications in computer science. In compiler design it has got an application, and many other locations. In operating system it has got an application, in distributed systems it has got an application, in networks it has got an application. So we are looking at some of these graphs, and many of the graph theoretic algorithms and graph theory that we spoke about also talks a little bit about graphs without cycle, graphs with cycle and DAGs. So a directed acyclic graph is a directed graph. Okay, we already know what is a directed graph. A directed graph, the edge has an orientation, but it has to be without cycle. So an example is this. Please note, because it is directed, now normally in an undirected graph this is a cycle, but when you take a directed graph you can go from here, this is a path, this is a path, this is a path, this is a path, but at no point can you come back to the one where you have started. So from here you can go here, but you cannot come back to this. From here you can go here, but you cannot come back to this. From here you can go here, but you cannot come back to this. So in this way this is not a cycle, though it will look like a cycle to you. If you consider this as an undirected graph, it is a cycle, but when you look at a directed graph, please note the definition of DAG says it has to be a directed acyclic graph. A directed graph which has no cycles. So this is an example of a DAG. Now let us go to what is called a weighted graph. So a weighted graph is a graph with numbers assigned to its edges. So and it could, what is this weight? What are these numbers representing? It could be cost, it could be distance, it could be travel time, it could be hop. This hop is very important when we talk in a network application, where whether you can go from one node, position or one node to another node without going through another node. So the number of hops from one node to the other and so on. So there are a lot of concepts that you can associate with the weights that you use for representing the edges. So a graph algorithm or a graph representation is very important in many applications of both electrical engineering, computer science engineering, electronics engineering, and even mechanical. Okay. So now this is an example of a weighted graph. If you look here, again here we have taken a weighted graph that is undirected. Okay. So 0 to 2 it is 20, 0 to 1 the weight, this could be cost to travel from 0 to 1, it could be the distance to travel from 0 to 1. Please note, cost and distance need not be directly proportional, and then travel time, time to travel and hop and so on. So if you look here, this is weight is 20, 10, 1, 4, 5, and based on this comes the question of the shortest path or the least weight path that you can, shortest if this is associated with distance. So normally that is how they talk about that algorithm, but it could be the shortest in terms of time, it could be the least cost in terms of cost and so on. So now let us go to another topic, which is the representation of graph. Before we go into the representation of graph, we will take a short break. Welcome back after the break. Now before the break we had looked at the basic definitions of graphs. We had looked at graphs, directed graphs, undirected graphs, we had looked at weighted graphs, we had looked at a special type of directed acyclic graph, which was a directed graph without cycles, which was called DAG, and then we have looked at some terms associated like vertices, edges, degree of a node and so on. Now let us look at a representation of a graph, because we are talking about data structures, and when we want to do any of the operations on graphs we have to necessarily represent the graph, and so let us look at how graphs are represented. Basically you have two types of representation, the adjacency matrix representation and the adjacency list representation, again which could be a sequential list representation and a linked list representation. Basically the adjacency term comes from the fact that if you have an edge between A and B, you call them as adjacent, and so both the representations basically has to represent whether there is an edge. When you say that they are adjacent, you mean that there is an two nodes are adjacent. V and let us say X, A and B are adjacent. When do you say A and B are adjacent? You say A and B are adjacent if it has an edge between them. Okay. So, that is how we talk about adjacency. Basically these two are different this is a 2-dimensional representation, this is also a 2-dimensional representation, but in a different way. This is basically supposed to be less storage than adjacency matrix. This is especially important when the size of the matrix is very large. So, suppose you have a 1000 node graph, then you have to have, according to adjacency matrix, you have to have 1000 into 1000 as the matrix size. While here the representation is only for edges that exist. So, we will come to that, you will understand it better when we are talking about the actual representation. So, let us go to a simple representation. If you have n nodes, okay, I will tell you how to do this representation later. If you have n nodes, then you have to have an n into n 2-dimensional array, where n is the total number of nodes or vertices, and it is essentially a binary matrix, where 0 says that there is no adjacency between the two nodes or no edge exists between the two nodes, and 1 if there is an adjacency, that is there is an edge between the two nodes. Here we are assuming that the weight is 1. So, that is why you are able to have a simple simple binary representation matrix, and here the nodes it is a directed graph. Okay. So, it is a directed graph, but not a weighted graph. Now, let us take the example. So, I have 1, 2, 3, 4. What we have to do is actually all these are represented by zeros. Now, suppose I have a edge between 1 to 2, then in 1 and 2 position 1, 2 I will put a 1. Now, next I have 2 to 3. So, there I have 2 to 3. Next I have 2 to 4. So, here I have 2 to 4. Then next I have 3 to 1, 3 to 1. Then I have 3 to 4. Then I have 4 to 1. So, actually before this 1 comes here, there are the whole matrix, 2-dimensional matrix is filled with zeros, initialized to be zeros, and then as their edges come, we are representing as 1. Please note, altogether there are 16 entries here, or it is a 16 sized 4 into 4 size matrix, and but actually you are using only 1, 2, 3, 4, 5, 6 locations. So, you can understand this is only a simple 4 node matrix. If you have a 1000 node matrix, it is a 1000 into 1000 representation, and of that most cases it is a sparse matrix. I suppose you know what is the meaning of sparse matrix. Sparse matrices are matrices where most of the entries are 0 and only very few entries have some value. Here is 1, it could be some value also. Now, look at this adjacency matrix. Let us see how to represent the nodes in the adjacency matrix. Assume there are n nodes in the graph. So, you have to use a matrix 0 to n minus 1, 0 to n minus 1. This is an n into n matrix. If vertex I and vertex j are adjacent or there is an edge between them, then aij is equal to 1, otherwise aij is equal to 0. If vertex I has a loop, that is there is an edge from I to I, then aii is equal to 1. If there is no edge from I to I, then aii is equal to 0. So, this is the basic principle of the adjacency matrix representation, and so this is an example of in the terms of aij. So, now let us take another example, 0, 1, 2, 3, 0, 1, 2, 3, and the nodes are also represented, and you see that 0 to, this is, please note, this case it is a case of a 0 to 2, 0 to 2 and 2 to 0. This is a case of an adjacency matrix representation for an undirected graph. So, 0 to 2 and 2 to 0, 0 to 2 and 2 to 0, 2 to 0 and 0 to 2 both will have 1, ij and ji, and 0 to 1, so on you can build the whole graph. So, if it is an undirected graph, most of the entries may be filled also. So, this is the matrix that you get out after you represent this. This is an undirected graph. The previous example we saw was a directed graph. Please note the difference is in an undirected graph, if there is an edge between 0 to 2, you have to put in 0 to 2 also 1 in the place and 2 to 0 also 1. So, aij is equal to aji is equal to 1. So, that is what you have to do in the case of undirected graph. So, directed graph, again we have already seen an example. This is another example of 4 nodes, and in the terms of Aij you find that here 0 to 2 you have 0 to 1 you have a edge, 0 to 2 you have an edge, that is it. Then you have 2 to 3 you have an edge, 2 to 3 you have an edge, 1 to 2, 3 you have an edge, 1 to 3 you have an edge, and so on. So, this is straightforward, we have already seen an example before. Now, this is a different, now we are moving off from binary matrices to non-binary matrices. So, this is exactly similar to what we did in the previous case, except that now you have associated weights. This is an undirected weighted graph. So, again you have weights associated. Instead of putting 1 here, we are putting the actual weights. Okay. Again you see that 0 to 1, 1 to 0 is there. So, 0 to 1, 1 to 0, both have 20, both have 10, and so on. Please note here that in the case of undirected, not weighted, unweighted graph, you are actually assumed that this weight is 1, all weights are 1. Here we are actually putting the weights. So, this is a matrix, adjacency matrix representation for an undirected weighted graph. Now, let us go to the another representation, which is the sequential adjacency list representation. Now, here you have the vertex number, which is the node number, and the degree is the number of nodes linked to this node, and then you have an adjacency list which shows the nodes linked to this node. Please note, this is just a representation of the graph in another way. So, now we are taking only a directed graph example, unweighted. So, now let us look at this 1 number of nodes linked to this node. So, you have 1, the degree is, you have 2 things, 2 edges going out of it. So, the degree is 2, and then you have the adjacency list saying that 2 and 3 are those 2 nodes. Now, let us take 2, from 2 you have 1, 2, 3 out degree, 3 you have. So, you have 3 degree 3 here, the nodes 3, 4, 5 which are there. Then if you take 3, you have only 1 edge going out of 3. So, you have the degree as 1 and that node, actual node. If you take 4, you have node edges going from 4. So, you have 4 and 0. 5 if you take, you have 1 and that is 1. So, this is a simple representation. Please note, this represents the vertex number or the node number or actually A, B, C, D or whatever it is. This represents the number of edges coming out of that particular node, and this is the actual list of the nodes to where it is going. So, 2 you have 3 things going out of it and it is going to 3, 4 and 5. So, this is another representation of the same graph. Now, here what happens, let us go to the previous case. Here what happens is the size, basically why do we need representations? We need only we want to reduce the size of the representation. So, this is a way in which we have done. But again here you can use arrays, it is called sequential adjacency list, and so it can be, what you are using here are arrays or a list, a sequential list. But here you have a linked list, array of pointers of size equal to the number of nodes. Each pointer in the array points to a linked list of nodes. Now, here the array is used only to give a pointer to its neighbors. So, suppose you have n nodes, the size of this array is n. So, suppose you say 1000, you will have only 1000 as the size of this array, but in the adjacency matrix case you had 1000 into 1000 which is much higher. So, here you have 5 nodes, you have 5, this is the same graph that we saw for the sequential list. Then here you have, so if you have the first node, you go to the first location. This is like an array indexing, we have seen this before. So, this will have a pointer to a list, again a linked list, and this pointer, this linked list will contain the nodes to which it is adjacent. Now, let us take a case of 1. So, 1 you have 2 nodes, so you have 2 and 3 represented there. 2 you have 3, so you have 3, 4, 5 represented there. 3 you have 1, so that is represented. 4 you have no node, so its pointer is null, and then 5 you have 1, so that is represented here. Now, here you will note that you are actually representing a node twice, even in the previous case we were doing that. If there are, but this is a linked node of a linked list, you 2 nodes point to 3, so you have 2 entries in the linked adjacency list. So, again we have seen the weighted list. Now, this we are looking at the weighted list represented using the adjacency list representation or the linked list representation we saw previously. So, you have 0, 1, 2, 3. Similarly, this is the pointers to the nodes But look at this, in this node, in addition to having the node value, you also node number, you also have the edge weight. So, this 10 tells you that the weight of the edge between 0 and 1, is 10, okay, and 0 and 2 is 20. Okay. Now, look at this we have taken a case of an undirected graph. Okay. So, if it is 0 to 1, you also have 1 to 0. So, that is understood, and again it will have 10. So, here this shows the actual weights. So, you have a node which is represented using node number, the weight of the edge between 0 and 1, and a pointer to the next node. So, this is a linked list representation of a weighted undirected graph. Okay. So, the comparison of the representation is given two vertices u and v. If you want to find out whether u and v are adjacent, then the time is only 0, 1, and the degree of the node is in the adjacency list it is equal to the degree of the node. In the, if you want to enumerate all the neighbors, it is 0 of n, and this is the degree of the node 0 n. For all vertices, enumerate all neighbors of each vertex 0 n squared. It is the summations of all node degrees 0 of v. Here this is 0 of n means degree of that node from where you want to find out. So, this is adjacency matrix obviously much more effectively much more, but the time taken is efficient, it is very efficient time wise, but space wise it is not very efficient, which we have already discussed. Now, let us go to another major application of graphs, which is called as graph traversal. In graph traversal, what we do is we list out all the cities that United Airlines can reach from Hartford Airport. So, this is Hartford, which is called the source. You have something called source and destination when we talk about traversal. This is the source. Now, what we do is for graph traversal, we start from vertex u and list all vertices that can be reached from that u in the graph G. So, that means the set of nodes now expands, and each node has a flag to indicate that it has been visited or not. I will come back to, I will indicate what we mean by this. Remember, traversal means we have already seen tree traversal, you visit a node only once. So, in the step 1, what you do is find the neighbors of Harvard, which is NYC and CHI. Then now what we do, you find all the neighbors of CHI, which is CF, LA, NYC, but NYC you do not put again in the list because NYC has already been taken care of. From NYC again CHI you have, you do not consider that, and so on. So, this way you build a graph. So, you have this, now you have Harvard, Chai, this. So, you are finding the neighbors, plus please note you are finding the neighbors and you are putting in the node only in the list only if it into that set, only if it is not already there. So, finally, you land up with this and find the neighbors of LA and SF. So, there are no other new neighbors. Okay. So, finally, we get all cities that United Airlines can reach from Harvard Airport by that algorithm, which is called the gas traversal algorithm. So, here you have mark all nodes as unvisited, pick a starting node, add u to the probing list. While the probing list is not empty, you keep adding the neighbors, and if it is not if it is unvisited, add it, otherwise do not add it. So, basically there are two algorithms, depth first and breadth first. We have already seen depth first and breadth first searches of trees. Here we are just looking, start from the first node, visit adjacent node moving in depth. Once last node is visited, backtrack one, and similarly breadth first. So, you can just look at this, the principle is the same that we used in trees. So, define the following terms: shortest path, directed graph, weighted graph, and given the following, please represent this graph using a adjacency matrix. So, in this lecture we have basically spoken about the graph, its definitions, basic operations that you do, and the graph terms that we used, the representation. We looked at 3 representations of graphs, and then we looked at a typical algorithm associated with graph, which was called the graph traversal algorithm. Thank you.